studied systems with tDCS. People have studied this for changes in MEP amplitude. And a typical stimulation intensity of 1 milliamp during tDCS induces a very weak electric field. It's on the order of 0.1 to 0.5 volts per meter. That's a very weak electric field. The direct effect of this very weak electric field is that it polarizes cells' membrane potential. So I guess this is a bit hard to see, but the in the nodal case, during a nodal DCS, which is thought to increase the excitability of the motor cortex or your target brain region, the soma is typically depolarized during a nodal DCS. During cathodal DCS, the soma is hyperpolarized, which is thought to reduce the excitability of the target brain region. Along with this somatic polarization, there's also dendritic polarization, right? And the dendrites tend to be polarized opposite to that of the soma. So if the soma is hyperpolarized, the dendrite is depolarized. And if the soma is depolarized, the dendrite is hyperpolarized. Now, based on classical animal literature, the change in the excitability, let's say just in the motor cortex, because that's where it's been studied in depth, both in the classical animal literature and most of the early studies in tDCS in humans have been also done in the motor cortex. So in the motor cortex, the nodal DCS tends to increase excitability, and it may be due to this change in the somatic membrane potential. And you'll notice that for a typical layer 5 pyramidal cell, which is possibly the most sensitive to the electric field, it's only polarized by about 0.2 millivolts per volt per meter. Now, that's extremely small change in the membrane potential. If you think about a cell that's at rest, to get that cell from resting to firing an action potential, you need about 15 millivolts of depolarization. So how can something so weak that induces a 0.2 millivolt depolarization move a cell to firing? And ultimately affect brain function. One way a very weak electric field can modulate excitability and have changes, long-term effects, is by changes in the synaptic activity, right? And so we can study synaptic activity and how electric fields modulate synaptic activity in a reduced preparation in vitro. So we go to the motor cortex, we take brain slices, and we measure the synaptic activity in the form of these field potentials, which is the marker of synaptic activity. So with presynaptic stimulation, we take an electrode, we stimulate the fibers, and we get a marker of synaptic activity in the form of these field potentials. Now, if you think about training, what happens during training, there's this ongoing activity in a particular pathway. So we probe a pathway during continuous synaptic stimulation, right, in order to emulate the training condition. And so we reach this steady state evoked potential in these brain slices. And when we turn on the field, the immediate effect of the electric field is an increase in synaptic activity. This is an extremely well-characterized result, both in, especially in the animal data. It's an immediate increase in synaptic activity, which then we show is sustained during DCS. And this is one of the novel findings that we've shown, that as long as the field is on, the change in synaptic activity is persistent. Now, moreover, this effect on synaptic activity is polarity specific. So like I showed you, during a nodal DCS, the soma is depolarized. That tends to be associated with an increase in excitability in our experiments. So the size of these field potentials, some markers of synaptic activity, is increased. Right? And that corresponds to somatic depolarization, which then ultimately leads to a change in the excitability of your target brain region. Similarly, cathodal DCS, which hyperpolarizes the cell, tends to reduce synaptic activity and reduces overall excitability in that particular brain region. And this change, so we can in brain slices, we can apply different intensities of electric fields and look at how the sensitivity changes with changing amplitude of the electric field. And we find that it's about 1% change in the responsiveness of these cells per volt per meter, in the synaptic activity per volt per meter. If you consider a case where there's training, there's ongoing activity, on a cellular level, that's a particular pathway that's being activated at a particular frequency, right? So there's synaptic input coming in, and that synaptic input accumulates, tends to have a cumulative effect on the postsynaptic cell. And what happens during DCS is that due to the depolarization, the direct effect of the cell, of the electric field on the cells, there's a greater accumulation on the postsynaptic of synaptic activity. So for instance, in this trace, you see memory potential. The memory potential sums up with synaptic input, right? So there's a greater residual depolarization, but during DCS, that depolarization is even larger. Right? So there's the cumulative effect of DCS. So although DCS has a very weak effect, it induces a very weak electric field, has a very weak effect on single cells. When they're embedded in a network and there's synaptic activity, this very weak effect can ultimately be amplified due to synaptic activity. So what I showed you, these effects are primarily dominated by somatic and dendritic polarization, right? Because somatic polarization changes the likelihood that the cells will fire an action potential. Dendritic depolarization is really critical because that's where the synaptic inputs come onto, right? So you can affect synaptic activity by polarizing dendrites in addition to polarizing the soma. But there are other structures in this brain region besides somas and dendrites. And that's where a lot of the literature, basic animal literature from the 50s and 60s have really focused on this idea that, you increase somatic, you increase excitability by polarizing these cells and their somas. But there are other structures, for instance, axons and their terminals, in the same brain regions as where you have these somas and dendrites, right? And these axons come in and they terminate on these dendrites. And in fact, these axons, as we've shown, are highly susceptible to polarization, right? And their synaptic terminals are the most sensitive. So they can be 2 to 3 times more sensitive to polarization than the soma, right? Which has very important consequences for synaptic activity. So one hypothesis is that in an electric field, if the axon itself is polarized, you change its sensitivity, you can drive synaptic activity through polarization of these axons, right? More recruitment of axons. So with that hypothesis, we can go back to a reduced system and design an experiment where we can directly probe how many axons are being recruited in the cortex during an electric field. So we apply a very strong stimulus to a bunch of axons in the cortex, in the primary motor cortex, in rat brain slices. And we do this in the presence of an electric field, right? And we measure the fiber volley. Now the fiber volley is a response. The amplitude of the fiber volley directly correlates with the number of axons that are generating action potential. And you can think of this external stimulus that we apply as a TMS pulse, right? Because TMS pulse comes in, it might recruit more axons, and we try to see how can an electric field modulate the number of axons that we've recruited. And it turns out that DCS affects the number of synchronously active axons by modulating its sensitivity, the sensitivity of the axons, not just of the postsynaptic cells, the somas and dendrites, but also of axons and their terminals, right? So axons and their terminals are also neuronal targets of DCS. In fact, recruitment of these axons during DCS directly drives synaptic activity. There's a direct correlation between the number of fibers that you're recruiting during DCS with an external stimulus and the size of the synaptic response. Right? So in addition to somatic and dendritic depolarization, these other presynaptic targets, for instance axons, play a really important role in driving synaptic activity. Now, we really focus on this target brain region, right? So there are these cell bodies and axons and their terminals in this target brain region. But where do these axons actually come from, right? So they're originating in some distant region. They don't have to be local cortical connections. These axons sometimes originate from very distant brain regions, right? And these brain regions are connected in a network where the activity of this afferent brain region drives the output from the target brain region. And if tDCS were to induce diffuse current flow, so current flow that hits both the afferent brain regions, where these axons are originating from, and the target brain region, well, you might imagine that can have that can drive the output from your target brain region. For instance, if your target brain region is the primary motor cortex, if the electric field is diffused and you're trying to hit the primary motor cortex, but the electric field hits premotor, now you can drive the output from primary motor cortex by affecting premotor. Right? So diffuse current flow may affect disparate brain regions simultaneously, right? Because these cells are embedded across these structures, these cortical structures. And in fact, tDCS is not only weak, but it's also diffuse. Right? So the induced electric field, your target might be the primary motor cortex, but the induced electric field exists between your anode and your cathode. All of the cortical structures in between your anode and your cathode are subject to the electric field. And there are cells, obviously, in all of those structures. So any structure that feeds into your primary motor cortex is now a susceptible target for DCS. Right? And so the entire functional network that's mediating the output that you're measuring, for instance, if this is the MEP, it doesn't have to be the MEP, it could be any particular measure, right? The functional network may be entirely recruited by tDCS. This raises a really interesting question. If you're doing a task, how is tDCS functionally specific? How are you getting better at a particular task if the electric field is so diffuse, right? You might be hitting multiple brain regions simultaneously, yet the particular measure that you have is being improved, right? So this is a really interesting question. How is tDCS functionally specific? Well, one way we can approach this problem is to think about, well, what happens during training? During training, right, you have a particular network that's active, a particular functional network that's being activated, and there's endogenous plasticity. There's synaptic plasticity that's going on in that connected network. And so one hypothesis is that the electric field interacts with that ongoing plasticity. Right? So this is the hypothesis. The electric fields interact with the ongoing plasticity and might modulate plasticity to ultimately have an effect that's very specific to that functional network. Right? So put another way, the effects of tDCS may be brain state dependent. What you do matters. Right? So what you're doing during stimulation may ultimately affect the outcome. And so we can again go back to a reduced preparation, right? Go back to the brain slice and take this hypothesis and formulate it in a way where we can ask this question on a very cellular level and sort of build from the top, from the bottom up, right? And so we can design an experiment to test a very specific hypothesis that during DC stimulation, the endogenous plasticity will be modulated, right? So the first thing we have to do is induce this plasticity. And one way to do that is using a very well-characterized system in the hippocampus by using theta burst stimulation. These are bursts of action potentials arriving down a particular synaptic pathway, and specifically this is the Schaffer collateral pathway in the hippocampus, which is an exhaustively studied for plasticity. And theta burst stimulation induces very robust and long-lasting synaptic strengthening, LTP. And so again, the hypothesis was in the presence of an electric field, this ongoing plasticity might be modulated. So we apply an electric field that depolarizes the soma, right? In this case, the inputs are timed precisely when the soma is maximally depolarized. And guess what happens? There's a robust increase in the amount of plasticity, right? So synaptic strain is modulated during ongoing plasticity. So the electric field modulates LTP, which is our initial hypothesis. Right? So now the synaptic inputs that come in when the memory potential is maximally depolarized at the soma, this can promote LTP. So this brings us to the state dependency of brain stimulation. So that's a very big point. That this is the first time anyone has shown really, that ongoing plasticity can in fact be modulated by an electric field, right, in vitro. So I've told you about diffuse current flow. That diffuse current flow, well, it's going to target your target brain region. It's going to affect your target brain region, but it'll also hit your afferent brain regions, right? So diffuse current flow then may bias the entire active system, that functional network, towards plasticity by promoting activity in both brain regions. The underlying state of the activated brain region may potentially influence the effects of brain stimulation. With that, the more we understand these cellular mechanisms, the better we can design clinical therapies. We can design rational therapies. For instance, I gave you a hypothesis on how we might achieve functional specificity by modulating endogenous plasticity, ongoing plasticity. And one way we've approached this problem is by starting at the cellular level. By studying these cellular mechanisms, we can then rationalize experiments to do in humans, for instance, where we can have training, endogenous plasticity, and modulate that ongoing plasticity. But there's a big gap here between the cellular mechanisms and the cognition and behavioral effects that you observe in the clinic, right? And there's a need to bridge this gap that I think some of the following speakers will address. But one way we might approach this problem is through developing a framework where we take our knowledge of animal literature, these effects that we observe on single cells, on synaptic activity, and on plasticity, and combine it into a quantitative framework so that we can provide predictions and analysis to interpret the clinical data. With that, I'd like to thank our funding sources and you for your attention.